Hi, welcome to the talk about PyART, an approach for real-time API recommendation in Python language. My name is Xinchun He, a PhD student from Nanjing University. This is joint work with students and professors from Nanjing University and Purdue University. PyART provides a list of Python APIs in real time for a given recommendation spot. Here, a spot means a recommendation point in the form of caller.api. In Python, it means invoking a method of object caller. For each point, only the context before the recommendation point is given to simulate real-time scenarios. In our example, assume the developer is about to invoke the get method. Given the preceding context as shown in the shaded box, PyART recommends a list of functions on the right. The task is challenging, in part because of features of Python language, such as type dynamics, static analysis limitation, and path sensitivity. Furthermore, real-time requirements pose additional challenges, such as incomplete context, lack of code histories, and cannot afford high overheads. Facing these challenges, API recommendation approaches based on learning tend to have better performance. However, they have some limitations. Visual Studio IntelliCode is a state-of-the-art recommendation tool for Python. It's learning-based. We use it to demonstrate a number of limitations of such methods. Then we motivate the design of PyART and shows the different recommendation results. Firstly, the ability to recommend APIs is heavily dependent on the type inference results for the objects of the API call. Consider the example on the slide, which calls data from a URL. The URL is requested after the object calls requests callback function by calling the API GET. IntelliCode produces no recommendation for the recommendation point of quotes. The reason is that it cannot infer the type of caller object. In contrast, PyART can suggest API candidates from different aspects, and hence it would not yield an empty list, even if the type inference is not successful. And in this case, it suggests a number of APIs with the correct one ranks first, with 60% probability. Secondly, even if the object type can be successfully inferred, it's possible that the recommendation list generated by IntelliCode only contains candidates in the alphabetical order. The main reason is that learning-based approaches do very well in recommending frequently called APIs, but not the project-specific ones. For this limitation, instead of depending on frequent patterns, PyART also considers multiple hints in the current context to help make a prediction. Consider the example on the slide, which tests status of the object self by invoking the method crawl defined in the class of self. PyART collects data flows related to the recommendation point and considers the co-occurrence of each candidate and tokens in flows, and finally suggests a number of APIs with the correct one ranks first. Therefore, we propose a novel API recommendation technique designed explicitly for Python. Given a Python code context, PyART first identifies the recommendation point. Then, it performs static type inference for the caller. If the type inference is successful, it takes all the callable methods of the inferred type as candidates. Otherwise, it collects candidates from 3 sources, including standard libraries, imported third-party libraries, and all the callable methods in the current scope. We want to point out that failure of type inference in real time is very common. For each recommendation point, the feature collector then analyzes the source code to collect hints about the current context. This is a challenging step. Firstly, due to the dynamic nature of Python, there are very few static analysis tools that can provide accurate results for Python in a cost-effective manner. And then secondly, in the context of API recommendation, it's necessary but difficult to deal with partial code. Therefore, PyART features an efficient way of extracting optimistic data flow from incomplete Python contexts. Such a data flow is neither sound nor complete, but sufficient for API recommendation and cost-effective to collect. The idea is to simulate how humans reason about data flow, different from traditional data flow analysis. Consider the example. It collects all entry points of backends and reads each point with a method load. Traditional data flow analysis attempts to obtain information at the boundaries of basic blocks and considers entry state and exit state of each block, and uses control flow to determine how a value is propagated. This is, however, difficult for Python. In contrast, humans infer data flow based mainly on local symbol information. For example, they consider surrounding variables. such as the variable namespace manager in the same line, the variable entry point, PKG resources, and iterate entry points in the previous context. In addition, humans infer data flow based on program structures. For example, in loop structure, there is a data flow from PKG resources dot iterate entry points to entry point. In the assignment, there is a data flow from entry point to namespace manager. Therefore, PyART defines rules to derive approximate data flow from 5 basic abstract syntax units, including assignment, loop, object attribute access and invocation, container access, and function parameter passing. Since the 5 units may occur in combinations, rule aggregation aggregates the data flow relations derived from individual units. In addition, PyART models the effect of flow following the propagation rule. For example, if there is a data flow about X in line 1, it will be propagated in other locations about X after the line 1. And the preservation rule retains all the data flow relations whose variable method objects are not affected by a unit and hence should be killed. Based on collected features, the encoder then generates a feature vector T with 4 elements, including optimistic data flow hints, token similarity along data flow, co-occurrence of an API with objects that invokes the API, and co-occurrence with other tokens. Spatially, PyART learns the order of tokens with optimistic data flow hints, which trains a statistical language model (NGRAN) on plenty of data flow paths containing APIs, and gives log possibility score as an element of feature vector. In the training process, the model constructor performs supervised learning using random forest. We evaluate PyART with 5 research questions, including the effectiveness of PyART in data flow analysis, recommending APIs within and across projects, efficiency of API recognition, and feature importance analysis. For evaluation of data flow analysis, we choose an advanced static analysis for Python named Python 2 as a baseline, and we use manual inspection as the ground truth because there is not an existing tool that can report sound and complete data flow information. For the API recognition evaluation, we firstly choose Visual Studio IntelliCode, an experimental set of AI-assisted developer productivity tool, as the baseline. And we reproduce a state-of-the-art API recognition method for Java named APIREC and port it to Python as another baseline called PyART. For data flow analysis evaluation, the average precision, recall, and F-score of PyART are both higher than 95%. In contrast, Python 2 has extremely low recall from 8% to 28% and has some runtime failures in a few cases too. Since the baseline PyART is not applicable without histories, we set different evaluation scenarios. For API recognition evaluation, for intra-project recognition with histories, PyART's average top 1 accuracy is over 50%, and the average top 10 accuracy is over 70%, and outperforms PyART and IntelliCode for top K accuracies. For intra-project recognition without histories, PyART also shows better overall performance than IntelliCode, and outperforms IntelliCode by 10% for top 1 and top 10 accuracy. It's important for API recognition tools to make cross-project recognition for more generality and usability. For cross-project recognition, PyART shows better overall performance than IntelliCode and PyART and outperforms baseline for top K accuracies. For efficiency evaluation, the average API recognition time of PyART is generally lower than 1 second, hardly noticeable. This is very important to satisfy real-time requirements. For feature importance analysis, we observe that each kind has a non-trivial positive contribution to the accuracy. For 6 out of the 8 projects, accuracy is most heavily affected by the optimistic data flow feature. Due to time limitations, we skip the discussion of related work. To summarize, we derive optimistic data flow that is neither sound nor complete, but sufficient for API recognition and cost-effective to collect. And we use 3 kinds of features: data flow, token similarity, and token co-occurrence, and also develop a method to encode them to feature vectors. We develop a prototype PyART based on the propose idea and evaluate it on real-world projects. The evaluation results demonstrate that PyART can provide effective API recognitions. This concludes my talk. Thank you very much for listening.
Okay.
Hello, everyone. So we are back. Thank you, Xing-Cheng Hu, for the presentation. It's a really inspiring work. So we are open for questions. So if you have any questions, please feel free to type in the chat. I don't see any questions related to this paper so far. I will start with one. So, Xing-Chen, can you help us clarifying a little bit how the optimistic data flow approach actually is? So can you give us some more details about that?
Thank you, Chair, for your kind question. We call our data flow analysis optimistic since we think our data flow analysis is neither stable but sufficient for API recommendation in Python language. This idea is to simulate how humans reason about data flow in real-time scenario. It's supposed to be correct and largely precise. Our hypothesis is that it is efficiency to build a joint distribution for API prediction. Especially, humans infer data flow based on local symbolic information, such as surrounding variables or program structures, and really, and in most cases, they reason about analyzing that is obscure or global. However, this is different from traditional data flow analysis. Since according to the definition of traditional analysis, it aims to gather information about the possible states of values calculated at various points in a computer program, and program's control flow graph is used to determine these parts of a program to which a particular variable or value assigned to a variable might propagate. The traditional analysis also considers the entry states and the exit states of basic blocks. However, might be difficult in the real-time scenario since the syntax and the semantics of the Python code is incomplete. So, since the dynamic of Python language, variables can be changed in anywhere, and the global variables can be changed by local models. So it is quite difficult to collect correct data flows by traditional static analysis, and this is the reason why we define the optimistic data flow for our API recommendation scenario. Thank you.
Thank you for the really thorough answer, Xing-Chen. So I see some questions in the chat. So Michael Pradel is asking, can you elaborate a bit more on the comparison with Intellicode? In particular, for what kind of recommendations does your approach or Intellicode work better?
Okay, thank you for the question, and this is a great question. In our motivation, we provide, in fact, there are 3 kinds of motivation examples that we can work better than Intellicode. The first one is the recommendation points that the type of objects cannot be inferred correctly for the recommendation point, and in this case, Intellicode cannot provide any recommendation results since it collects candidates based on the inferred type. For Intellicode, in this case, we collect candidates from different aspects, and hence we would not yield empty lists, and we can get a great answer for this kind. And second, since the Intellicode is trained intelligently for based on a large corpus. So it learns frequently used patterns. So if the recommendation point wants to invoke a specific, a project-specific API, which is defined in the current projects, in most cases, IntelliCode cannot provide better recommendation, since it cannot find a specific a suitable pattern which can match this scenario. So in this case, we can work better than IntelliCode. But in fact, IntelliCode is very great for the frequent pattern recommendations, such as some frequently used APIs, such as list dot append, string dot, some callable methods of basic types. It works much better. That's all. Thank you.
Okay, thank you for the answer. If you have any follow-up, Michael, please go ahead and ask your question. So I have a question from Jawei. It's a clarification question. How about the execution efficiency of your approach as it's for real time?
Okay, the real-time requirement is very important for the API recommendation scenario, and this is very important in when it works as an IDE plugin. So the recommendation time of our approach is the average time is less than 1 second. This time consists of future generation and the probability score of each candidate's generation, and the list ranking for the output for to the developers. However, we didn't record some preloading time, including preloading the project and make a very simple static type inference for the for each variable in the current context, and this is finished in the preloading time. And once this the preloading process is finished, we will not need to do it again when we recommend each APIs in different recommendation points in the current projects. Thank you.
Thank you for the answer, Xinjing. So I have another question, since there are no other questions in the chat. So after reading your paper, I was with a feeling that okay, you use contextual information as a feature of your model, right? So how big does the contextual information need to be to provide accurate predictions, accurate suggestions? Did you analyze that?
Do you mean the effects of each kind of feature of our approach?
Your approach, for your approach.
Our approach makes use of 4 kinds of feature vectors. The most important one is optimistic flow, since it is very important to gather information about the values of variables in the static analysis. The second, the token similarity of tokens in the data flow, since it is more it is to simulate human it is to simulate how humans reason about the API. Since, for example, if we invoke API logger.getLogger and we assign the return value to a variable, the variable usually is named as logger. So the similarity between the return value and the invoked API is very useful for our recommendation. And the third one and the fourth one feature vector is about the co-occurrence.